Hello everyone. In this lecture we are going to discuss about reducing disaccharides. So in the previous lecture we have seen about what are disaccharides and the classification, and also we actually discussed about non-reducing disaccharide and also example of non-reducing disaccharide sucrose. So in this lecture we are going to discuss about the reducing disaccharides and few examples of reducing disaccharides. So the reducing disaccharide basically consists of, if you see the classification, the reducing disaccharides also known as glycosylaldoses or glycosylketoses. So these are reducing. Why? Because they consist of aldehyde and ketone functional groups in this structure. So these are classified into two types based upon the glycosidic linkages. So some reducing disaccharides have C1 to C4 glycosidic linkage and some have C1 to C6 glycosidic linkage. So let's discuss the examples which comes under C1-C4 glycosidic linkages. So the very first example will be lactose. So lactose is a disaccharide. It is purely of animal origin. It is commonly called a milk sugar present in milk. So it is present in mammary glands. As mammary glands secretes milk, so the milk is rich in the lactose sugar, and it is also found in urine during pregnancy. It is less soluble in water. So lactose can be hydrolyzed by the action of enzyme called lactase, and this lactose will be hydrolyzed into glucose and galactose. So intestine of milk sucking infants has the abundant amount of lactase enzyme. Why? Because the infants actually feed upon mother's milk for few months to 1 year. So that's why the intestine of infants consists of lactase, and the lactase is essential for the conversion of lactose sugar into glucose and galactose. Then only the disaccharide or the lactose, upon conversion into glucose plus galactose, then only it will be absorbed into the body. Excess of lactose in the milk ingested into the body causes watery diarrhea. So this excess amount of lactose in the milk causes condition known as a diarrhea, and also abnormal intestinal flow and colic pains. So here colic pains actually occurs in the abdominal region, which means around the intestinal region. So this intestinal pains or colic pains, intestinal flow as well as diarrhea are a serious issue when there is an excess amount of lactose present in the milk and is ingested into the body. So this lactose exhibits mutarotation due to the presence of carbonyl groups on the carbon atom 1 of glucose unit. It is formed by the elimination of a molecule of water from the glycosidic OH group of beta D galactose and the alcoholic hydroxyl group on the carbon atom 4 of D glucose. So here it exhibits the mutarotation as it consists of a carbonyl groups at the carbon atom 1, as well as it is actually formed by the formation of glycosidic bond between beta D galactose and D glucose. So let's see the structure. So this is the structure of beta D galactose. This is the structure of beta D galactose, and this is beta D glucose. You can point out the differences in the structure. So here the arrangement is different in case of beta D galactose, right? So the linkage between these two units, which means the hydroxyl, actually the glycosidic bond forms between these two units of sugar. So when you see, this is actually a C1 C4 glycosidic linkage. Glycosidic linkage. It's a C1-C4 glycosidic linkage. So let's see how the C1-C4 glycosidic bond will be formed. So this is carbon atom 1, 2, 3, 4, 5 and 6. Here 1, 2, 3, 4, 5 and 6. So upon the reaction, this one water molecule will be eliminated from these rings, leads to the formation of glycosidic bond. Here comes the glycosidic bond. So exactly the glycosidic bond actually formed between the two rings at carbon atom 1 and carbon atom 4 of beta D-galactose and beta D-glucose. So this is how the lactose formed from the beta D-galactose and beta D-glucose. So next example will be the maltose. So here maltose is a disaccharide. It is commonly known as a malt sugar. So malt from sprouting barley is the major source of maltose. So generally this maltose actually is actually from the sprouting barley is the major source of maltose. So the some seeds like seeds and grains are the rich source of maltose, right? So this maltose is known as a malt sugar, which actually abundant in case of sprouting barley and other seeds and grains. So how the maltose is formed here? So the starch upon the action of enzyme known as alpha amylase, starch can be broken down into dextrins and maltose. So here starch is a polysaccharide, right? So the polysaccharide upon the action of an enzyme known as alpha amylase, so the starch can be broken down into dextrins plus maltose. So as maltose is a disaccharide, it must be broken down into monosaccharide in order to body to absorb the carbohydrate more efficiently. So the maltose upon the action of the enzyme known as maltase, it will be converted into two molecules of D-glucose. Then only it will be absorbed by the body. So here we need to remember that whatever the carbohydrate form, either it may be a polysaccharide or disaccharide, after we consume it, it has to be broken down into monosaccharide units. Then only the body will be able to absorb the carbohydrate more efficiently in monosaccharide form only. So here maltose is a reducing sugar. Maltose is a reducing sugar. It reduces Fenling's solution and Tollin's reagent. This shows the presence of free aldehyde group. So it is a reducing sugar. Why? Because it consists of functional groups, and when upon the reactions like Fenling's solution and Tollin's reagent reactions, this shows the presence of a free aldehyde group. So that's why it is known as a reducing sugar. Upon the reaction with reagents like Fenling's and Tollins, it will form the other compounds which will be characterized by the presence of free aldehyde group. It may be formed by the removal of molecule of water from the glycosidic hydroxyl group of alpha D glucose and the alcoholic group on carbon atom 4 of another D glucose. See here we can understand like this. So here also you can observe the C1-C4 glycosidic linkage. Glycosidic linkage here. So the maltose can be formed by the formation of glycosidic bond between alpha D glucose and alpha D glucose. Is it? See, you can observe here the bond actually forms between 1 and 4 carbon atoms by the loss of one water molecule, leads to the formation of maltose like this. So this is the structure of maltose, consists of 1,4 alpha glycosidic bond. So these are examples for the C1-C4 linkages. C1-C4 linkages of reducing disaccharides. And the final example apart from lactose and maltose will be cellobiose. It is one such reducing disaccharide, consists of C1-C4 glycosidic linkages. So cellobiose is a disaccharide identical with maltose. It is present in tracer amounts. It is released during the digestion of the polysaccharide cellulose by cellulases, which means cellobiose, which is a disaccharide, upon the hydrolysis it will give glucose units. So here this is the structure of a cellobiose. It is actually formed by the formation of glycosidic bond between beta D glucose and beta D glucose units, and it has a composition of cellulose. So it is released during the digestion of polysaccharide cellulose by cellulases. It can be released by the hydrolysis of cellulose by the action of cellulases enzyme. Like this is the cellulose, which is again a polysaccharide. Upon hydrolysis by the enzyme known as cellulases, it will give cellobiose. So this is the structure of the cellobiose. So cellobiose on further hydrolysis. So let me show you. So cellulose is a polysaccharide, right? Cellulose is a polysaccharide. Upon hydrolysis by the enzyme called cellulases, it will give cellobiose, which is a disaccharide, right? So this disaccharide must be converted into a monosaccharide. So upon hydrolysis, on further breakdowns, this is converted into glucose units. So this is how the cellulose and cellobiose actually processed into monosaccharides. So these are the few examples of reducing and non-reducing disaccharides. So I hope you understand this lecture. Thank you.